this video, we're going to be talking about how to find the equation of a tangent plane. And we've been given the function z is equal to x squared plus y squared. And we've been told that the point of tangency is the point 3, 4, 25. So keep in mind that this is just a transition or an extension of single variable calculus where we learned how to find the equation of the tangent line. So in single variable calculus, we had a two-dimensional curve, and we would be asked to find the equation of the tangent line, which was the line that just skimmed across the graph at one single point. Well, here we have a three-dimensional function, it's a surface, and we've been asked to find the equation of the plane that just skims across the surface, intersecting it at only one point. And that point is going to be 3, 4, 25. So the formula that we're going to use to find the equation of the tangent plane is this formula here. And the important thing to remember is that most of what we're going to need for this formula we already have. So for example, we're going to take x1, y1, and z1 directly from the point of tangency. So x1 right here is going to come from this x value in the point of tangency. y1 is going to come from, of course, the y value. And z1 is going to come from the z value. So we have those three things already. X, y, and z in this formula we're going to leave alone. They are going to remain in our final answer, which means that the only two things left to find are the partial derivatives of z with respect to the variables x and y. Keep in mind also that not only do we have to find those partial derivatives, but we have to evaluate those partial derivatives at the point of tangency. And the results that we get are going to be the values we plug in for these partial derivatives in the formula. And these partial derivatives evaluated at the point of tangency really just mean slope in the x direction and slope in the y direction. So let's go ahead and do that. Let's go ahead and find the partial derivative of z with respect to x, and we're going to find the partial derivative of z with respect to y. So with respect to x, remember, because we're taking the derivative with respect to x, we treat all other variables, in this case y, as constants. So y is going to be treated as a constant, which means the derivative of y squared is going to be 0. The derivative of x squared will just be 2x, so we'll get 2x plus 0, or just 2x. Same thing now when we take the partial derivative of z with respect to y. We hold x as a constant, so its derivative will be 0, and we treat y as the variable, so the derivative of y squared will be 2y. So we'll get 0 plus 2y, or just 2y. So those are going to be our partial derivatives, but now we have to evaluate them at this point before we can plug them in to our formula. So evaluating the partial derivative of z with respect to x at the point 3, 4, 25 is going to be 2 times x. Well, x is just 3, so 2 times 3, or 6. So this is the value we're going to plug in for partial derivative of z with respect to x. Here we're going to evaluate the partial derivative of z with respect to y at the point 3, 4, 25. So we're going to get 2 times y. Well, y is just 4, so we're going to get 2 times 4, or 8. And this will be the value that we plug in for this partial derivative of z with respect to y. So now we actually have everything that we need. We can go ahead and say that this value is going to go in for partial derivative of z with respect to x, and that this value is going to go in for partial derivative of z with respect to y. So now we're just plugging everything in. So we're going to have z here, starting with our formula, z minus z1, which is 25. So z minus 25 is equal to partial derivative of z with respect to x, which we found was 6 when we evaluated at the point of tangency, multiplied by x minus x1. x1 comes from the point, which is 3, plus partial derivative of z with respect to y, we found that to be 8, multiplied by y minus y1. So y minus, y comes from the point, that's 4, so we plug that in. And this is the equation of the tangent plane. Most often it's going to be simpler to multiply everything out on the right-hand side and solve for z on the left. So here's what that's going to look like. Z minus 25 is equal to, distributing the 6, we get 6x minus 18. Distributing the 8, we get plus 8y minus 32. If we add 25 to both sides and combine like terms, we're going to get z is equal to, we'll put the x first, so 6x, then the y plus 8y, and then we got rid of this negative 25 over here by adding 25 to this side. So now we have negative 18 minus 32, that's a negative 50, plus 25 is a negative 25, so we end up with a minus 25. And this then, z equals 6x plus 8y minus 25, is the equation of the plane that's tangent to this function at the point 3, 4, 25.